So welcome everybody to our theory of gamma seminar, sorry. Today we have the pleasure to guest Tymon Frelik from the University of Warsaw, who is going to talk about an introduction to Cartan geometry. So Tymon, thank you for accepting our invitation. Please go ahead, the floor is yours.
Thank you for having me. So yes, today I'm going to talk about a branch of differential geometry that's very dear to my heart and which is one of my favorite research fields in differential geometry. And I will do a very basic introduction to this subject. So let us start with a motivating quote from Élie Cartan himself. In the wake of the movement of ideas which followed the general theory of relativity, I was led to introduce the notion of new geometries, more general than Riemannian geometry, and playing with respect to the different Klein geometries the same role as the Riemannian geometries play with respect to Euclidean space. The vast synthesis that I realized in this way depends, of course, on the ideas of Klein formulated in his celebrated Erlangen program, while at the same time going far beyond it, since it includes Riemannian geometry, which had formed a completely isolated branch of geometry within the compass of a very general scheme in which the notion of group still plays a fundamental role. And indeed, here is a diagram from a textbook on Cartan geometry by Richard Sharp. So one takes as the starting point Euclidean geometry in the realm of linear algebra. And so obviously one of the possible generalizations that we know of linear algebra is the curved analogues. So in the Euclidean case, that would be Riemannian geometry. But indeed, historically, it has been the case that another generalization has been towards group theory proposed by Klein. And both ways, from Klein geometries and Riemannian geometries, in the case of Riemannian geometries taking a group-theoretic approach, one can kind of develop a theory of Cartan geometries. And in the case of Klein geometries, one can consider kind of curved analogues of those and also arrive at Cartan geometries. So this is the general idea that I will want to outline in my talk. So let us first recall very basic definitions on principal bundles. Namely, we consider a manifold P on which a Lie group H acts freely and properly, right? So on the quotient space of P by H, we have from the free and proper action, we have a smooth structure of a manifold. And as such, considering this quotient projection, we have our bundle. So we will refer to M as the base space. And one of the important features of a principal bundle is that given our action of H on a manifold P, as here, and an evaluation of this action at a point U in P, right, which gives at a point a map from the Lie group to P, one can define the differential of this action and evaluate it at a Lie algebra element. And in this way, one obtains the so-called fundamental vector fields, which are the vector fields on the manifold P, which corresponds to the action generated by the infinitesimal Lie algebra elements corresponding to the group action. Yes. Now we want to also make known some definitions from Lie group theory. The first one being the Maurer-Cartan form on G, And so a Maurer-Cartan form is a one form on the group valued in the Lie algebra, defined such as here with respect to the left action by an element, any element G in a group. And the key property of the Maurer-Cartan form is that it satisfies the Maurer-Cartan equation given here. The use of this equation is that it carries the information about the structure of a Lie group, which is in some sense equivalent to the commutation relations given by the commutator of the elements of the Lie algebra, right? The C's with free indices we refer to as the structure constants. And indeed, the structure constants appear as well in the Maurer-Cartan equations, which are in some sense the dual carry the dual information to the information carried by Lie algebra elements, right? So in kind of the differential geometric picture, it's a classical fact that one associates Lie algebra elements with left invariant vector fields on the group. And so analogously, one can make an identification between dual Lie algebra elements and left invariant one forms valued in the algebra. So now we will introduce the notion of a Klein geometry. So a Klein geometry is a pair consisting of a Lie group and its closed subgroup, such that the quotient is connected, the quotient of G by the subgroup H. So oftentimes a Klein geometry will be understood as just the homogeneous space itself. The Cartan theorem on a closed subgroup assures us that the quotient G over H carries the structure of a smooth manifold. Additionally, since we do have a smooth manifold structure on the quotient, one can consider the canonical projection from G to the quotient space, and this indeed has the structure of a principal bundle with H being the structure group of this principal bundle. And also, if we consider the Maurer-Cartan form on the Lie group G, it satisfies the following properties, which I will list here since they will be important in making a generalization to Cartan geometries, right? So on each fiber, which we identified with the H action, the Maurer-Cartan form is linear. Then under elements of H, since this is an H principal bundle, it transforms as given here, right? Here is the pullback of the form by the right action of an element H. And here we have the adjoint action. And also the key property that we have already highlighted is that it maps fundamental vector fields to the corresponding Lie algebra elements which generate the H action that we consider, right? So let us bear in mind these three properties because we will next develop kind of a curved analog of those. So one can also look at the structure of the tangent space in a Klein geometry. So here is a classical picture of a short exact sequence that one associates with fiber bundles. So the rows are exact in both cases. So as we said, Cartan form makes an identification between the tangent space of G with Lie algebra G. Then passing on to the quotient, we have another identification as here, and also an analogous identification on the fibers, right? So here this sequence splits as vector spaces, and we establish isomorphisms with kind of the bundle sequence above. And this is also a key property that we will generalize in the Cartan theoretic case. So as we said, we can make an identification of the tangent space of the base space of our Klein bundle with the quotient of the Lie algebras, G over H. But indeed, since we are considering cosets or equivalence classes, the identification we make with this map phi does indeed depend on what element G we choose upstairs, right? Which would then project to X on the base space. So we have this kind of resulting transformation property again with the adjoint action of H on our map G, which is inherited from the Maurer Cartan form. And we have the resulting proposition that the tangent bundle of the quotient may be identified as vector bundles with the fiber G over H as this. So yes, now we will proceed to define Cartan geometries, which are the curved analogues of the above construction. So by a Cartan geometry of type GH on a manifold M, we will mean an H principal fiber bundle with the total space P and the base space M, which is endowed with a one form omega, which is G valued. And this one form we will call a Cartan connection, which satisfies the following properties, right? And these three properties kind of mimic the properties that we had with the Maurer-Cartan form. Yeah? So the first one is H equivariance, which is that property of transforming with respect to adjoint action of H, since this is an H principal bundle. Then we have that it reproduces the generators of fundamental vector fields, right? So for each fundamental vector field, we have an identification with the corresponding Lie algebra element in H. And another one is that it defines an absolute parallelism. So at each point U of P, we have a linear isomorphism of the tangent space with the Lie algebra G. But this is only at a point in the case of a Cartan geometry. So we will refer to the pair of a bundle, H principal bundle, and the Cartan connection that's defined in it as a Cartan geometry. So indeed, Cartan geometries do form a category, and an isomorphism of two Cartan geometries is a bundle map which satisfies this composition rule over the common base space M, and such that the pullback of the second Cartan connection is the original Cartan connection, right? So not much surprise here in terms of wanting to preserve the Cartan connection by an isomorphism.
Tymon, practically, if you have two Cartan geometries, you can say that they are isomorphic. Do you use some characteristic classes, or there is some theory particular to determine it?
No, actually, we don't need topology here since we have an absolute parallelism. So this is purely a local question. Is that the answer?
Yeah, really?
Mhm.
It's there are not different Cartan geometries related to
We're
such that.
on local questions here.
Okay,
Perhaps
thank you.
it's a topological interpretation involved, but yes, it will only be relevant for us to consider.
Okay, I see what you mean. Yeah. Oh, thank you.
Yeah. So this is at each point we have this isomorphism. So
Yeah,
in
you
this,
can compare every tangent space with the total space with the Lie
exactly.
algebra. So you have different. You have a
Exactly.
method to relate one to another. Okay,
Yeah.
thank you.
Yes. So we have there is a bundle map, and there is the form which at each point has this property of an absolute parallelism. So yes, so it's sufficient to consider local isomorphisms in this sense. So again, we want to generalize the picture of a tangent space to a Klein geometry. So again, this time maybe more familiar in terms of notation. We have a picture of a short exact sequence of a principal of a tangent bundle of a principal bundle. And again, the Cartan connection establishes this central isomorphism that we talked about. And then it descends also to an isomorphism on the base space, which the tangent space to each point on the base space we identify with the quotient of G over H, and then the analogous thing happens on the fibers where the identification comes from an appropriate restriction. And the transformation rule for our form for our identification on the base space is again given by the adjoint action for all tangent vectors downstairs. So we will often speak of a homogeneous model of a Cartan geometry, which is simply the Klein bundle associated with a group NS subgroup, which we model our geometry on. And so it is again endowed with a Cartan form. So this will also be sometimes called a flat model, and we will soon see why it's appropriate to speak of flatness in this case. But first, I just want to show for intuition a very nice picture of how one may look at Cartan geometries that's taken from this paper by D.K. Wise. So one can think of a hamster in a sphere which walks in the sphere consequently rolls this sphere over a surface, right? So if it were rolling that sphere over a flat surface, like a table, this would correspond to a Klein geometry, right? But we can put the ball with a hamster in it over some terrain, like a curved surface. In which case, we still consider the intrinsic geometry related with the hamster walking in the sphere, inside the sphere. But the curved terrain on which it walks corresponds to the deformation of the flat table, which we would associate with a Klein geometry. So a longer description of how this example illustrates Cartan geometries is contained in this paper. But the general idea is that we place emphasis not on the surface itself, as would be the case in Riemannian geometry, from deforming a Euclidean space into a Riemannian manifold, but we just look at the intrinsic rolling of the ball. Yes, and this is generally the picture that we want to think about. And this is unsurprisingly a geometry of type SO3 with H subgroup being SO2. And now we are in place to think of curvature of our geometries. Curvatures are defined by what's called structure equations, which are defined as such. So one may recognize that this expression here we already encountered in the case of Cartan forms. But in this case, we allow this term not to be zero, but to have some non-zero value. And this indeed corresponds to curvature, right? And in particular, we see that if we consider the Cartan equation on a Lie group, this indeed describes a connection with vanishing curvature. In this case, the Cartan form is the connection, which is flat since it obeys the Cartan equation. So there is a notion of a constant vector field, which this is which we denote as here. So the inverse of omega means that we are looking at which elements, which vector fields on P map to G, and we can kind of reverse this and look at what vector fields on the manifold P are given by Lie algebra elements X. And if we consider the homogeneous model of Klein geometries, unsurprisingly, we are able to reproduce left invariant vector fields. In the curved setting, if we consider elements of the subalgebra H in G, then we obtain the corresponding fundamental vector fields that are associated with our H principal bundle. And so one may see here, since the fibers of an H principal bundle are endowed with an H action, that the Cartan connection trivializes the vertical bundle of the total space in our bundle by the fundamental vector fields of that H action, right? So one may pass on to consider constant vector fields, and consequently, instead of considering a two-form, a curvature two-form on the total space of our bundle valued in G, we can consider a curvature function which maps from the manifold P to this tensor product, right? So homomorphisms from the second exterior power of the Lie algebra G to G. So this identification is given by this formula. And indeed, one can, again, look at this as kind of a perhaps deformation of the commutator bracket on the algebra by a curved term which is given by the Cartan connection, right? So this is kind of the algebraic way to think about curvature, which is indeed very useful, as we will see. But there is also, as in the case of connections, there's the notion of a torsion associated with a Cartan connection. So we have seen that the curvature form is a semi-basic form in the sense that it vanishes when evaluated on vertical vector fields. And indeed, then one may view the curvature function as a map, not to the second exterior power of G dual here, but one can take the quotient G over H, which again we identified with the tangent space of the base space of our Cartan bundle, right? So so this is the kind of reduction that we get in having just a two form on the quotient. And the torsion of a Cartan geometry is the curvature form, or rather the part of the curvature form, which is valued in G over H. And an important remark to be made here is that, yes, torsion is part of the curvature of a Cartan connection. And very often we are interested in studying geometries, Cartan geometries, which are torsionless in the sense that the curvature function may be at each point interpreted as a homomorphism from this second exterior power now that we have on the quotient algebra to H, our structure algebra of the principal bundle. And the non-torsion part of curvature of a Cartan connection, right? So the so the parts that takes values in H more closely resembles what we usually mean by a curvature of a Cartan connection. And this will again be illustrated in the following example. So yes, we will consider a Cartan theoretic view of Riemannian geometries, right? So as we have announced in the beginning, one can look at Riemannian geometries as curved analogues of Euclidean vector spaces, right? So at each point, the tangent space corresponds to just Rn endowed with a Euclidean Euclidean inner product. And this is a local model for Riemannian geometries, right? So we may look at the group of isometries, which is the Euclidean group with the orthogonal group and the semi-direct product with Rn. So here we consider a group of rotations and reflections. And here we consider the group of translations. So it is indeed a matrix group, which one may realize as such. So here A denotes the orthogonal group component, and then the vector, the appropriate vector that corresponds to translations, right? And if we compose these matrices, it gives an appropriate transformation rule of rotations plus plus translations by vectors in Rn. Right? And a very simple observation is that if we take the quotient of the Euclidean group by the orthogonal group, then we obtain the vector space Rn that we are acting on. So if we consider in this sense curved deformations of this group theoretic picture, we do indeed get a Cartan geometry of type Euclidean group and orthogonal group, and such that the Cartan connection makes an identification of the tangent space on the base space with the quotient Rn for each x to which U projects in our ON principal bundle. So we can actually make a Cartan theoretic reformulation of the Levi-Civita theorem from Riemannian geometry, namely that up to isomorphism, there is a unique torsion-free, I emphasize that it's torsion-free, Cartan connection omega in the bundle P over M, such that our map phi is an isometry for all points in the total space, right? So, and also conversely, the Cartan connection determines the Riemannian metric up to a constant scale factor. So I will just want to explain why we have it up to a constant scale factor. Owen is a compact group, and its action on the one-dimensional subspaces of G over H is transitive. So by a classical fact from Lie theory, there is a unique up to scaling ON invariant quadratic form on the representation G over H, which we denote by Q. And if we fix a point in the base space of our geometry and choose a corresponding point in P upstairs, one can generalize this quadratic form to a smoothly varying metric on our manifold by this composition, taking the isomorphism at each U upstairs and then composing with our quadratic form Q, which gives an appropriate map from each tangent space to R. And this is independent of the choice of a point upstairs. So one of the obvious questions, and the answer to which I announced earlier, is how does the Cartan curvature compare to the traditional Ricci curvature of Riemannian geometry? So it's crucial that we're considering here torsionless geometries as assured by the Levi-Civita theorem. So we may regard this as a map given as here, since we talked about it that torsionless geometries are valued in H as two forms on the quotient Lie algebra here. So the identification of the Ricci curvature and Cartan curvature is given by the so-called Ricci homomorphism, which comes from a composition. So we start with our curvature function, then we apply identity on this component and the adjoint Lie algebra representation here. So we are placed in the endomorphisms of G over H. And then we apply a map which is defined as this. And so we obtain the familiar expression of something corresponding to the tangent space of the base space tensored with itself, which is indeed what we get in the Ricci tensor of Riemannian geometry. It is an injective homomorphism for in dimension 2, and it is surjective for dimensions greater than 2. So we will illustrate this example soon, but there is also one crucial point to be made here that, and this is something that everyone who has done general relativity kind of knows in comparing Minkowski space, de Sitter space, and anti-de Sitter space, which have similar symmetry, namely that the Euclidean model of Riemannian geometry is not the only flat homogeneous model that we can consider. There is also the hyperbolic model, which comes from taking as our group G the split signature or orthogonal group, and the spherical model, which comes from considering the orthogonal group in n+1 dimensions and quotienting out by ON. But in each case, our H principal bundle is an ON principal bundle, right? So the closed subgroup that we're considering is indeed the common structure group of the principal bundle. So something that we're observing here is known as modal mutation. So we want to make this phenomenon formal. So let us consider two pairs of algebras which will provide models for our geometry. In each case, H is common and G is different. So a mutation is an isomorphism of adjoint H modules, which satisfies that it's an identity when restricted to the subalgebra H, and also satisfies this kind of equivariance property modulo H subalgebra for all elements of G, right? So if we consider kind of the matrix form that we had for Riemannian geometries, so this was for the group. In the case of an algebra, we would just not have one here, but we would also have a vector here and a matrix in the orthogonal algebra. And so mutations in this case are given as this, right? So this is the Euclidean model that we had. The hyperbolic model has this matrix structure, and the spherical model has this one, which one may really arrive at by considering those different G groups in each of the cases. And so yeah, this is an analogous situation which happens with the constant curvature, de Sitter and anti-de Sitter spaces, and the zero curvature Minkowski space. So let us show some example computations that we get in dimension 2. So in this case, we consider the Euclidean group in 2 dimensions and the O2 subgroup. So the Cartan connection has this form. And the terms omega 1 and omega 2 correspond to the torsion, as we will see here. So Levi-Civita connections are just given by these omega 2 1 forms here. So the curvature is computed to be of this form. And again, torsions in this case are given by these two terms, which should vanish for Levi-Civita connections. And if we consider the structure equations here with appropriate curvatures, yeah, I should have K here. Then this coefficient in this place can be identified with the Gaussian curvature. That's a curvature invariant in a single one curvature invariant in 2-dimensional Riemannian surfaces. So we may also consider another example to kind of show that this theory extends far, far beyond a generalization of just Euclidean structures. So projective geometry is concerned with the study of the Klein space, with the group G given as the projective special linear group, which we quotient out by the center for appropriate dimensions. And the subgroup that we consider is the subgroup H of this matrix form with delta being an element of a multiplicative group of the real numbers. And so this corresponds to fixing a line in Rn+1, which corresponds to a point in the projective space that we obtain by projectivization of Rn+1. So we fix a point, and then we are able to make this quotient G over H. So indeed, the projective space has the structure of a Klein geometry by this mapping, right, from G to the quotient. And so here we obtain the homogeneous coordinates on the projective space. So the algebras that we consider are given by this coordinate expression. So A is a multiplicative parameter, which by the demand of the SL algebra has to be equal to minus the trace of this matrix cell here of size n plus n times n, and we have correspondingly elements of Rn here, right? And so for the subalgebra H that we will quotient out by, we just considering such elements of G such that Cj, the whole vector Cj, is vanishing, right? So this again corresponds to fixing a point in the projective space by this A. So we may write down the Mareur-Cartan equations of G. So we define a coframe with these coordinates corresponding to the appropriate matrix entries in the algebra G. So this constitutes a coframe on G. And the Mareur-Cartan equations corresponding to this matrix representation take this form. And indeed, each of the four families of equations corresponds to different matrix entries, which is useful since we can make an identification of some of these appropriately to the quotient that we take. We can identify some of those equations as corresponding to the fiber, and some of them as corresponding to the base space of our geometry, right? And so unsurprisingly, what we define as a projective structure on a manifold M is the corresponding Klein geometry of type projective special linear by a subgroup stabilizing a point in the projective space. And the Cartan connection establishes, so to say, deformations of these Mareur-Cartan equations. Hence, we gain curvature, right? And the Klein model in this case is the Klein model of the projective space. So there are very many applications of Cartan geometry, but just to give one example of applications of Cartan geometry in the case of projective structures is the applications to the theory of ODEs. So in considering RP2, one can define the bundle of contact elements, which consist of a pair of a point of the space, projective space, and a line that is one-dimensional subspace of our tangent space to the projective space. And this way we can consider the bundle of such elements, which may be identified with the quotient of G, the projective special linear group in 3 dimensions, by a subgroup, which is a subgroup of H of codimension 1, which fixes a specified line in RP2. So one of the results of Cartan was that a general second-order ODE on a 2-dimensional manifold M determines a canonical such geometry of type associated with the bundle of contact elements over this surface. So this gave a very interesting application in the theory of invariance of ODEs. One may define curvature of such a Cartan connection of type GK, and certain invariants which are associated with this curvature, when they vanish, then it means that the equation second order ODE that we were considering is of this form, and this has to do as well with the geodesics of the Cartan geometry that's given, but also Chern was able to generalize this to third order ODEs surfaces, and the geometry of a general third order ODE considered modulo contact transformations. Contact in the sense of the contact structure on the second jet bundle that the third order ODE is described on. Is described by a Cartan connection valued in the symplectic group of in 4 dimensions, but one may also restrict or rather consider equivalence by not by contact transformations but by point transformations, and in this case we obtain a geometry valued in a Cartan geometry valued in the conformal group plus R3. So
sorry, Tymon. Yes, a couple of questions, okay? Because for certain second-order differential equations, you have, for example, geometric functions or things of the sort. Do you know any application or any description of these differential equations in terms of Cartan geometry?
Once again, the application.
You know, there are certain second-order differential equations of the sort you gave, okay?
Yes.
So some of them, they are related to so-called, locally, they are related to the so-called hypergeometric functions or things of the sort. So the question is if you know any type of application of Cartan geometry to these particular cases of differential equation.
So these differential equations, here we have a single equation by dimensional reasons, but these equations here of second order,
yeah, if you determine the coefficients A, B, C, D, you get some famous differential equations. So the thing is, if you know any further results about what Cartan geometry says about these particular differential equations, this is my question.
Well, these describe geodesics of projective structures.
Yeah, but if you fix the coefficients A, B, C, what can you say about these geodesics? They are a particular type, or do anything else?
Yes, in general, and one can also make this characterization in terms of different values of curvature. Yes, so one looks at the matrix expression of curvature, and one looks at which cells, appropriate cells of the curvature matrix have entries, and then one can also make a classification. Of ODEs in that respect, and it goes also beyond just ODEs. It also gives a rich representation theoretic description of PDEs as well in many cases. So it's a very rich subject. But just for the case of projective structures and second and third order ODEs. It's kind of outlined in the book by Sharp. It's only outlined there. This third order equation case is obviously in the paper of Chern, but there is also a very nice paper which talks about this geometry in the modern language by Nurowski and Godliński on the third order differential ordinary differential equations, and then there is the kind of algebraic description of those types of third order equations. Yeah, obviously the most relevant relevant feature here is that depending on the geometry that's associated to a kind of a differential equation, we can speak of symmetries of a differential equations by relating them to
the Cartan geometry.
yeah,
One question: when you talk about second order differential equations, you talk about second order differential equations in normal form. Yeah, I mean when the second order differential term, the second order derivative is written as a function of lower order derivatives of you can get any other type of description.
So if I understand correctly,
what do you call a second order differential equation? I mean, there are second order differential equations where the second order differential of the variable, like the one you have written in here, yeah, are written, they are equal to a function which depends of the lower derivatives of the unknown and the independent variables. You see that it's always like that, or you can have something like y dot plus cosinus hyperbolic y dot times y dot equal to 0, you know, because sometimes you cannot put it this way. You know what I mean?
Yes. I would have to think about this. It's a good question.
Okay, because there is another.
In any case, these are rarely the kind of the most symmetric, and in this case, from the point of view of symmetry, interesting equations. But from the point of applications, they definitely are. It's a good question, but one always passes to the jet space, right? And one considers formulation of these equations of jets, and that's where the geometry comes from.
Okay, because you know, even if you in the jets space formulation, many of differential equations people are worried about, or they care about, for example, about the pi level property or things like that. Normally they are not in normal form, okay, or they are in normal form passing to some compactification of a manifold, something like that. You need some kind of trick,
right? And there's also, in the case of Cartan geometries, there is the famous fascinating method of equivalence by Cartan, which is in a sense an algorithmic method for establishing equivalence of geometric structures. And so if one considers the equivalence method associated with the ordinary differential equations, then there is a notion of canonical coordinates, which in some sense may correspond to normal forms of equations.
One thing, maybe there is a typo, yeah, in the geometry in the last paragraph about the third order differential equations, the function method, it depends on x, y dot, yeah, and y dot dot.
Oh, yes. This should be y, yeah, y.
Yeah, okay.
Yes.
Yes, in normal form, as you said before. Okay, so
yes, this is y dot.
Thank you.
And so I will just very quickly want to make some
yeah, sure.
comment on the references. So this talk was primarily based on the textbook of Richard Sharp, Differential Geometry, Cartan's Generalization of Klein's Erlangen program. but one of the kind of modern Bibles of Cartan geometry is the book by Andras Chap and Jan Slovak, Parabolic Geometries, which deals kind of with a very special and algebraically nice kind of parabolic geometries or Cartan geometries, which are named parabolic geometries, since in that case the subgroup H of a Cartan geometry is taken to be the parabolic subgroup, right? So a subgroup which contains the Borel subgroup. And this book has a lot on this kind of representation theoretic algebraic approach to this subject, and a lot of really beautiful, rich results. And then there is also the book by Ivy and Landsberg called Cartan for Beginners, but in kind of the Cartan geometry community, it's notorious for being a very difficult book, but it's primarily deals with exterior differential systems and Cartan-Kähler algorithm for exterior differential systems. And one comment that I would want to make here is that one of the remarkable facts about Cartan geometry is that a lot of these results by Cartan have been established far before a modern notion of a fiber bundle or even a connection in a bundle has been established. So Cartan was indeed working with exterior differential systems, and it's definitely remarkable and beautiful that he was able to make these come up with these results, which are very meaningful geometrically and algebraically. Right, and yeah, this is all I have to say for today. Thank you.
So thank you, Tymon, for your nice talk. It's been very clear to me. I didn't make too many questions because we discussed previously a little bit this, and also I think that everything you said, it was very clear. So anyhow, is there any other question, remark, comment to the speaker today?
I do have a quick question. Could
Yeah,
you go
sure.
back? Okay, could you go back to the definition of the Cartan connection, please?
Here.
Okay, great. In what sense does this define a connection? I mean, does this give you some sort of principal connection or an Ehresmann connection or something, or is
It's a connection, yeah. So it's obviously different than Ehresmann connections. It gives a connection in the sense that one can lift vector fields. Well, most notably, it's a connection in the sense that it gives a splitting of this short exact sequence, right? So we have the split short exact sequence given algebraically on algebras, and if we make an association. An isomorphic association at each level here, then we have a splitting of this bundle, and all the classical properties of a connection follow, right? So we can talk of horizontal vector fields. One can talk of lifts by our connection form, yeah. So this is kind of the.
okay? So you do get some connection from the
Yes,
Cartan connection. Okay.
definitely. It is a connection in the truest sense.
Okay, okay. And in what is the curvature of this true connection, let's say, of the connection in the Ehresmann sense related to the curvature in this sense?
Yes, I mean, if you in the non-Cartan case, if you consider the geometry of frames and kind of the connection on the frame bundle, which is a obviously a principal bundle with an appropriate structure group, right? So if you have a Riemannian metric, you have an SON principal connection. Without a metric, it's a GLN principal connection. And so this expression for curvature is also there in the case of like general G structures. If like beyond Cartan connections, right? So if you consider G structures and connections on them, or principal bundles, and that's also how you express curvature, right? And it's kind of a beautiful relation that you can give this a meaning in terms of the more Cartan form.
Okay, thank you.
Thank you.
So here's one comment. Summarizing what Tymon said, that it is right indeed. It gives a natural connection in the way of the making and splitting of the total space. Normally, principal bundle give you the splitting by means of the kernel of the curvature connection. Here is a little bit more complicated because the inverse image of elements of the Lie algebra H give you the vertical part by making a supplementary. These are the vertical one, the constant one. And by making a supplementary to H, you can always obtain some splitting. So this is the way it works. And the structure of the omega with respect to the action of the group H allows you to do this in an invariant manner. This is more or less the idea. It's a little bit more complicated, but richer than in the case of the principal bundle case.
Right.
So it's what Tymon said, but in another manner. It's essentially
right.
what.
And a nice kind of an expository comparison in a sense, which has a kind of a rich section on principal bundles, G structures, homogeneous spaces, is in the first chapter of this book, right? So it's good for comparing those definitions.
Yeah, and here's one comment from some of us, because there is a potential application of these two Lie systems, as I said to you, Tymon. Once you take a look at how far one could go, because it's a topic known from the 80s, 90s, where all the systems were described by means of mostly almost every Lie system could be described by means of homogeneous spaces. When one has a Lie system, there is a Lie algebra vector field. In the most important cases, this Lie algebra spans the tangent space. And this allows you to write the manifold like quotient of a third Lie group with isotropy group of a point. But the projection from the Lie group to the quotients gives you a Cartan geometry. Okay, you have the isotropies of groups, you have the total group, you have a third connection, you have a third projection, a Lie group action, and this allows you to recover third structure of Lie systems. There is a lot of work about describing or classifying Lie systems by means of these, but no one talks about Cartan geometry. There are something like 20, 30 works by means of Witterning and 13 types of Lie systems, and they are all about considering a certain Lie group with a certain Lie subgroup with certain properties, and it looks pretty much the same as these. So I don't know how much can be done to describe the system by means of Cartan geometry, but many things you did, Tymon, you explained, they look similar to other things that they appear in these works, but the language is different. I mean,
it is a different language, and indeed, I think it's historically different. I mean, these ideas have their roots in Lie, and then obviously Lie systems were kind of developed by Vesua, right? And then Cartan was also a student of Lie, but this is maybe kind of a side remark because you spoke of papers by Winternitz on Lie system. One of the early tour de force applications of the Cartan method was his so-called 5 variables paper, in which he considers generic rank 2 distributions on 5 manifolds, and associates to, in the modern language, associates to them a G2 valued Cartan geometry, right? So it is indeed an example of a parabolic geometry, right? Because it's a G2 divided out by a nine-dimensional parabolic subgroup, which gives a 5-dimensional manifold in the flat case. And I know that Winternitz, I think, has a paper on those parabolic subgroups.
Yeah, he has lots of papers. Winternitz, I don't know how many papers he has, maybe 800, 1,000, something like that. It was crazy. And about this, he has an epoch in the 80s, 90s, and he was working a lot about this topic. Then I asked him why he stopped about that in this way. And I don't know, I didn't get any final answer. From my experience, he was disappointed that it didn't draw so much attention as he wanted. And then people started worrying about other types of topics. But yeah, it has lots of things about things similar to this. So, okay, so I was about to say something. There is also something about these forms, these Maury Cartan forms, these curvative forms. This is just a curiosity, okay? I don't know how much this is important, because sometimes when you write them, I noticed that some of them, when you write in coordinates, you will see much better in example. But the one you wrote, for example, in this example, it does not work. But in other examples I saw, they look a little bit or much like K-contact structures. It was fun to me to find something of this sort. So it was kind of interesting that they look much like K-contact. I don't know if there is any relation or if somehow they appear. There is some kind of thing you can do, but yes, it's a comment aside, okay?
It would be definitely interesting to make a connection between those two.
Yeah, I mean, it's not general, because in general it does not give you, but in theoretical work, when I took a look at the forms you get, the curvature forms you get, many of them, they are very similar. I don't know why. Okay, so that's all. Any other question, remark to the speaker? No. So thank you, Tymon. Really, it was very nice, and it was pretty clear to me, everything. So I like it a lot. Thank you. So see you in a week. Maybe we have still a last speaker before Christmas.
Yes. Next week we have Julia, who I don't know if she's here, but she was here.
Yeah, a while ago. Julia is here.
Yeah, she's here. And she will talk about current algebroids.
Yes, exactly.
Okay. So it's like with Awiya, she appeared finally. So thank you, and see you in a week, the last before Christmas.
Bye, see you. Thank you for attending.
Bye.
Nice talk, Tymon.
Bye.
Very nice talk.
Yeah, thank you, Tymon.
Thank you.
Thank you.